بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. أهلا وسهلا بحضراتكم في الويبنر الأول للمركز الأفريقي لإدارة مخاطر الكوارث ADMiR African Disaster Mitigation Research Center في إطار مشروع تعزيز القدرة على مواجهة الكوارث في الدول العربية من خلال نماذج متعددة المخاطر وخرائط التعليم الآلي وأجهزة استشعار الإنترنت الأشياء. معلش، هو عنوان المشروع طويل شوية. النهاردة بيشرفنا الدكتور ماء العينين البيضاء من المدرسة الوطنية للعلوم التطبيقية بوجدة، جامعة محمد الأول في المغرب. هيكلمنا النهاردة عن تطبيقات التعليم الآلي في خرائط مخاطر الفيضانات الحضرية. أعتقد مخاطر الفيضانات من المخاطر اللي بتزداد أثرها بشكل كبير، بالذات مع تأثيرات التغيرات المناخية ومع زيادة هشاشة المجتمعات تجاه تلك المخاطر مع تكراريتها وقوتها المتزايدة في الفترة الأخيرة. كان مهم جدا إن احنا ندعو العينين، وهو أحد الشباب الباحثين بالمغرب، علشان يدينا فكرة عن دراسته اللي بيقوم بيها من خلال رسالة الدكتوراه تحت إشراف الدكتور ميمون شراق الأستاذ الزائر بالمركز، والشريك الأساسي في المشروع بالطبع. بدون الإطالة في المقدمة، أنا هترك المساحة لماء العينين في البداية علشان يعرف نفسه، بعد كده يدينا المحاضرة الشيقة ديت. طبعا المحاضرة مسجلة وهتكون متاح تسجيلاتها من خلال موقع المركز إن شاء الله. وطبعا في نهاية المحاضرة هيكون في فقرة للأسئلة وللاستوضاحات، فلو أي حد عنده سؤال سواء يكتبه خلال الشات أو الكيو أند اي، أو في نهاية المحاضرة هيكون عندنا فقرة للرد على التساؤلات. ماء العينين، يعني أترك لك المجال وتقدر تعمل شيرنج للمحاضرة بالنسبة لك. اتفضل. آه،
السلام عليكم. يس.
وعليكم السلام. احنا هنسمعك بوضوح وشايفين دلوقتي الشاشة بتاعتك. اتفضل.
So, hello everyone. I'm excited to welcome you to this webinar hosted as part of the ARICA project. And this initiative focuses on enhancing disaster resilience in Arab countries through advanced modeling and mapping using technologies like machine learning and Internet of Things. And this webinar is titled The Application of Machine Learning and Urban Flood Hazard Mappings, and where I will explore the potential of this technology in transforming the landscape and approach in flood risk management. My name is BaidaNational, and I'm thrilled to be presenting you today along my supervisors, Professor Oujda and Professor Mohamed and Professor Mohamed. And this team is a collaborative effort between myself, Professor Oujda, Mohamed, and Professor Mohamed. So the urban flood hazards are increasingly pressing issues, which are driven by two main factors, which is climate change and rapid urbanization. With climate change, we're seeing more frequent and intense rainfall events, which can quickly overwhelm the city drainage system. At the same time, the rapid urbanization reduces the filtration of urban areas, which, of course, these factors increase the risk of flooding in urban areas. With several factors, of course, several studies have emphasized and detailed and explained how this combination of the two, which is the climate change and the urban expansion, in aggravating and increasing future flood risk. So the importance of hazard mapping is that before the urban expansion, it's essential. It's essential and important to understand how the city designs influence flooding. And by using three-dimensional modeling allows us to visualize and predict the effects of different layouts in urban planning and helps us identify potential flood challenges. And after the urban expansion, the hazard map help the planners to manage these risks by providing essential information for safe city planning and zoning. And additionally, this hazard map supports effective evacuation and emergency response plans, ensuring that the city is prepared in the case of potential flood events. So the hydrodynamic simulation, of course, are the traditional way to assess flood hazard in urban areas. And they use detailed data such as digital elevation model, land use information, rainfall, etc. However, these are the two main problems with this approach. The first problem, which is the problem one, is that it can be very hard to get the necessary data, especially in fast-changing cities. The second problem, which is the problem number two, is that these simulations often take a very long time to run, which makes them impractical for quick decision-making during flood events. So to reduce the simulation speed, several techniques have been proposed, like the 2D capital model or the non-physical model, like the cellular automata model. While these techniques may help reduce the time it takes to run simulations, they often can't deliver the quick and accurate information we need when a flood actually happens. This means that during a rare flood event, the emergency responders may not have the time necessary to act quickly as possible. So in this case, we really need faster flood simulations. So to talk about the potential of machine learning in this context, and while the interpretation of a model is very important, in our context, which is the context of urban hazard mapping, we focus more on the speed of prediction. And since the machine learning are considered quote-unquote black box models, they can analyze past flood data and identify patterns and quickly emulate the flood hazard in urban areas. So the categories of supervised machine learning, when applied to the context of flood mapping, can be categorized into regression and classification. And of course, regression focuses on predicting continuous flood depth at specific location, which can help shorten the simulation time in hydrodynamic models and possibly provide a viable solution to the problem number two, which is the simulation time. On the other hand, for the classification models, they can predict hazard classes or hazard degrees, of course, just as low, medium, or high, which is particularly useful when the data is limited. And for plan one, which involves the data availability, classification allows us to categorize hazard without the need of detailed data measurements. So for the classification category, this image shows how different input factors are used to predict the probability or the likelihood for flood. And each layer on the stack on the left represents a different factors that influences the flood dynamics, like elevation, land use, slope, flow direction, etc. And on the right, these layers are transformed into a two-dimensional grid, which represents numbers such as 1 or 0, where 1 represents the presence or the probability of flood condition, and 0 represents the absence. The classification model then analyzes these factors to identify the patterns and determine the likelihood of flooding in each area. And by using historical data about flood presence or absence, marked by 1 or 0, this model can learn and predict flood per area across the landscape. And the purpose of using the classification model, of course, is to predict flood hazard without the need for complex simulations or complex data. And since most of the necessary inputs can be derived directly from elevation, like slope, the flow direction, flow accumulation, etc., and since elevation can be available online for any study area, we can gather valuable inputs for classification model for any study area. And since if we can leverage like the historical flood location and the inputs, which is abundant in the use for online remote sensing or data sets, we can map flood susceptibility or flood hazard at a large scale and very easily. But of course, the drawback of classification model is the absence of any quantitative data such as flood depth or flood velocity. So this slide highlights the two papers authored by him, and the first paper is a systematic review for all the classification models that were used in urban context. And in it, we identified the key inputs, the popular models, and the research gaps. And the second paper builds on the findings on the first paper. And in it, we applied all the results from the systematic review in a vulnerable case study. And the case study is the city of Zaya, which is located in northeast Morocco. And this region, characterized by its location in mountainous slopes, is particularly vulnerable to flood events. And to emphasize the seriousness of this issue, this slide shows a screenshot from a news article from 2007, reporting on a tragic incident where a girl drowned in a flood. This highlights the urgent need for effective hazard mapping and risk management in areas such as Zaya. So the inputs for the classification models in the case study use causative factors such as elevation and its derivative, in addition to distance to roads, to streams, flow accumulation slope, and SPI, which stands for the stream power index. And we integrate this data with the classification models to give the hazard probability, which raises from 0 to 1, with 0 meaning the low probability to 1 meaning the most highest flood probability or likelihood. And through the application of threshold, which changes the continuous probability from 0, 1 to a binary flood presence or absence. And interestingly, the classification model shows a very good alignment with other traditional methods such as HECRAS, which is a physical model, and CADIS, which is a non-physical model. So for regression, since the focus of regression models is simulation speed or simulation time, the first approach is to replace the traditional hydrodynamic models completely, also known as the surrogate models. And these models predict the flood depth quickly and are very, very, very ideally for large-scale assessments where a rapid response is crucial. But however, the drawback, the inconvenience is that these models may be less precise since they don't capture the detailed physics of water flow as the hydrodynamic models do. The second approach is to complement the hydrodynamic model using super resolution. And here we take the low resolution output from hydrodynamic simulation and improve them to a high resolution. And this method combines the speed of machine learning with the accuracy of a traditional method, and to give a balance between detail and efficiency. And it's ideal for scenario, of course, where both accuracy and speed are needed. But however, they are still slower than the forced approach, meaning that they are still slower than the surrogate models. So our systematic literature review of all of course, the regression models used in the context of urban hazard mapping revealed that the CNL model, of course, and the UNet architecture in particular, which was first introduced in 2015 for biomedical segmentation, has been popular and, of course, the most superior in terms of accuracy in comparison with other regression models. And this CNN structure treats the hazard mapping problem as an image-to-image translation. And when applied to the case study, our CNN model, we take a closer look at the details of this CNN approach. And this figure shows how the CNN is utilized to predict water depth in an urban area during flood events. And on the left, we see the different inputs, including elevation, slope, aspects, and soil curvature. And of course, all these inputs are insights from the systematic review, of course. And the insertion of these patches are processed after they were divided into patches of 2056 and 2056, because since the original unit architecture performs well on these sizes, these patches are processed by the CNN model, which uses this information along the rainfall hyetograph to predict the water depth for each passage. And then all these patches then are rearranged to create a complete map for the predicted water depth in the study area. And on the bottom right, the predicted map is then compared with the simulated map obtained through traditional hydrodynamic simulation. And the CNN model will aim to minimize the error between the predicted and the simulated water depth after multiple iteration. And of course, the model was trained on a dataset consisting of 8 simulations corresponding to different duration periods, and was tested on 4 simulations. And of course, after the training of the CNL models, you can show that either it reduces the computational time it takes to run both flood categories, which is the pluvial flood and the fluvial flood, from 2 hours and 31 minutes to just 1 minute and 15 seconds, leading to a remarkable 99% time reduction. And here in this video, we will demonstrate the flood depth reduction. As can be shown, we can dynamically adjust the rainfall, which we can obtain even before a flood can actually happen or during a flood. And the CNL model will be able to solution in 1 minute, making it a very valuable tool for evacuation, emergency response plan, and public awareness. The second is in regulation, which aims to complement instead of replacing for the computer fluid dynamics model, which grades for meshes to calculate water flow, and means that the more accurate the models it can capture details of water move downside. To improve accuracy, the time needed for reducing the grid size in half, which means that the correlation between the simulation time is exponential and non-linear. So using the machine learning model as we speed up and to low detailed simulation, which we can obtain and look like they will run on a high resolution grid, saving a lot of time without sacrificing too much accuracy. So the super resolution techniques have been traditionally used to enhance image and videos to improve their clarity and detail. And in our research, we proposed the version super resolution for flood modeling. We applied the EDSR CNN network to enhance the resolution for the study area. And the study area was divided like previously to patches of 128 by 120 patches to facilitate training. And of course, the CNN model will aim to improve the quality of the input by a factor. And this figure shows an example of enhancing a low resolution input by 64 by 64 input to 128 by 128 output, leading to doubling the quality of the image. It was after the division of the area into several patches, we test the CNN model on different upscaling. Specifically, we trained on 5 and 16. And after the training, the CNN model shows an impressive performance even at a higher factor of 16, since it preserved the fine details or the river section, which is the most critical in the count checks, as shown in the figure. From even at such high level of enhancement, this means that even from a low resolution input, the model could produce the high quality detailed flood maps that closely resemble the quality of the true high resolution simulation. And of course, this strong performance at 16 allows us to create accurate details and visuals over a large area locally, and as a result, a more rapid assessment. The presentation is that machine learning model can really strengthen our approach to flood hazard mapping, as it allows us to create pinpoint risky zones, which means that urban planners and decision makers can act faster and be more proactive in managing flood risk. And another key benefit is how efficiently the machine learning data by past flood information. This model can make reliable prediction even when detailed data isn't available. Then this is especially useful in urban environments where data can sometimes be hard to get. And finally, the machine learning helps improve the preparedness and response. And with better flood maps, cities can be better equipped to protect communities and save lives. ensuring that effective flood management uh, activities. And uh,
ثانك يو مايلاينين. شكرا مايلاينين، المحاضرة الشيقة والمعلومات الجميلة. وممكن نفتح باب النقاش لو في أي أسئلة. أنا شايف دكتور سيد مخيمر رفع. اتفضل دكتور سيد. لا، احنا مش سامعين حضرتك دكتور سيد. دكتور سيد المايك مش شغال. ما زال المايك فيه مشكلة يا دكتور سيد. طيب استاذن حضرتك دكتور سيد، ممكن تبعت السؤال في الشات. لحد ما دكتور سيد يبعت سؤال، هل في أسئلة تانية ناخدها لحد ما دكتور سيد يبعت السؤال؟ أنا كان عندي سؤال العينين إذا سمحت. هو يتعلق بالكمبيوتيشنال باور اللي بتحتاجها لعملية التريننج للماشين، والمدة الزمنية قد إيه؟
بالنسبة للCNN model for as بالنسبة للCNN training, it takes about 7 hours and 43 minutes before training, but after training it was similar for all data. So
ده
it's 7 hours. Yes.
ده باستخدام جي بي يو؟
لا CPU.
سي بي يو عادي.
Yes.
كم كور؟ أو
7 ساعات.
لا، how many cores for CPU from CPU?
5.
5 cores. So normal computer would do it in 7 hours.
Because يعني local authorities can't proceed, can't have a GPU. A GPU are very rare and hard to get for emergency planners. We decided, so this training on the CPU is on purpose, and we decided training on CNN and just it's time on a type of computer that is very common and very popular, which just its reliability.
So
But
you
for
decide,
GPU, these values can be very lower. And instead of 1 minute, for example, it can be several seconds for a GPU.
so you decided to make it on affordable computer, just
Yes.
any authority could have and could do the training and run this model easily. That's
Yes.
yeah. Thank you. That's very appreciated.
صباح الخير.
تفضل دكتور سعيد.
ألف شكر على هذه المحاضرة الشيقة يعني. أنا للأسف يعني I missed the first 10 minutes in presentation. I'm sorry for to be late. But my question regarding the training data, as you know that extreme rain event may be rare. So we have a small number of extreme rainfall. So how you can build your machine learning by using CNN, using few number of events. As you know that the machine learning, the accuracy of machine learning built mainly on the how many data are used in training your model. So this is the main questions. Maybe I have another question, but maybe after this point.
Okay. So for the training, so the training was done on eight different hydrograph, and as you can see, the hydrograph ranges from 10 or 15 millimeter to 15, which means that you can capture from even the smaller rainfall event to the large one. And of course, we changed the form from ECS type 2, which peak in the middle, to a more conventional one, which is the one following a rectangular form. So the test, so this training allows us to generalize to peak value.
She gave a good results.
Yes, exactly.
Okay. So another question regarding the inputs for your training model. As I think you present in only you enter training data is a static data, elevation, slope, aspects, but I don't see rainfall as an input for training model. Is it part of? It should be part of. I think so in the training model. So it's okay. But this is historical or time series rainfall.
So for the rainfall, we have the historical record station for the journal, the daily.
Okay.
Daily, and we did the statistical adjustment to obtain the different return periods. And of course, these daily rainfall return periods were then disaggregated using the different method. So this is.
Thank you so much. Thank you.
No problem.
السلام عليكم.
عليكم السلام.
أستاذ مسحب فريد من جامعة محمد الأول، المدرسة الوطنية للعلوم التطبيقية. شكرا العينين لهذا العرض القيم والجيد ومعلومات جيدة. أنا عندي سؤال فيما يتعلق بال Which machine learning model are most effective and predicting for short time flows based on real-time weather?
So for classification, of course, the ensemble models, which these ensemble models is a category of many types, like the random forest, extreme gradient boosting, etc. So these models have quantitatively proven to be the best in prediction flood hazard. This is for classification. But for regression, the CNN model was proved to be the best because it can treat as an image-to-image translation. It considers the corresponding nearby region, etc. So for regression, it's the CNN models, and for classification, is the ensemble models. And for example, for ensemble models, we mean random forest, extreme gradient boosting, etc.
داكور شكرا. مع العينين نستطيع ندخلوا الماشين ليرنينج algorithm to use the combined data from sensors, satellite imagery, and hydrogeological models for more accurate food prediction.
Yes, of course. So for classification here, as I said, for the inputs, most of the inputs can be derived from elevation. If we can have elevation we can have online to remote sensing. So elevation, if we obtain elevation, which is readily available from remote sensing data, we can have all the other, most of them, 90% of them. So while the elevation data from remote sensing can be less accurate from the other obtained method, we can leverage, of course, remote sensing to construct a database or inputs for the classification models. And this is where the two come in place.
شكرا مع العينين. شكرا.
شكرا جزيلا. هل من أسئلة أخرى؟
آم، أعتقد الصوت وقف عند دكتور محمد.
هل من... ألو.
الصوت وقف.
آه، معذرة، هل الصوت واضح دلوقتي؟ هل الصوت واضح؟ هل الصوت واضح دلوقتي؟ سيد. معذرة، حصل عندي مشكلة في الصوت. هل واضح الصوت الآن؟
نعم.
نعم نعم.
هل من أسئلة أخرى؟ هل في حد عنده أي مداخلة؟
السلام عليكم ورحمة الله وبركاته.
السلام ورحمة الله وبركاته.
شكرا جزيلا على العرض الشيق ده. وطبعا التوبيك ده احنا في المنطقة دلوقتي بقى حاجة مهمة جدا بالنسبة لنا، خصوصا ان احنا دلوقتي عندنا اللي كنا بنعتبرها رير فلاش فلادز، وايفنت بقت بتحصل وبشكل غير منتظم واوقات غير منتظمة. والمشكلة ان في شمال افريقيا زي مصر وتونس وليبيا والجزائر، اعتقد ان البنية التحتية الى حد كبير مش مؤهلة للاحداث المفاجئة دي. حصلت احداث كتيرة في الفترة الأخيرة في بعض الانفراستراكشر زي الليفل تيراسز او الجسور او بعض السدود، لكن هي مش مؤهله لكميات زي دي. فكنا حتى بنفكر بنراجع في بعض المودلز اللي موجوده زي السوات موديل او الفلوز او الكي دبليو في. وانا هنا سؤالي، طبعا انا مبهور بالعرض اللي اتقدم وكميه الانتجريشن بين الداتا. انا كان سؤالي طبعا هو من نقطتين. النقطه الاولى ان المحطات الارضيه قليله جدا في المنطقه بتاعت شمال افريقيا، هل هيبقى الاعتماد في الاساس على الداتا بتاعت الساتلايت؟ والسؤال الثاني، هل الموديل تيكن انتو اكاونت الدرينج اناليسيز والسويل كلاسيفيكيشن، خصوصا لو في لاند داتا فيلد داتا، لان عمليه الايريشن والران اوف دي مش ممكن مع الاخذ في الاعتبار الدرينج اناليسيز ممكن يبقى ايفنت صغير ويعمل دامج كبيره او العكس. وشكرا جزيلا لحضراتكم.
So for the all these parameters, of course, can should be considered in the hydrodynamic simulation. Of course, rainfall can play a very good even with the smaller events, and topography, of course, influences the flood hazard more than rainfall. And integrating detailed can be very difficult to get. And of course, here in the training, if the CNN model is trained with the accurate infiltration and accurate land use data and accurate training, it can be accurate. But if it was not trained on a very accurate information, it can be inaccurate and somewhat erroneous.
شكرا جزيلا.
يعني البريدكشن بتاع السينال موديل فيما يخص الانفلتريشن والى اخره يعتمد بشكل اساسي على الهيدرولينيشن اللي يتم الاعتماد عليها بالنسبه للتمرين الصياني. اذا كان غير 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 مفصل او ناقص بالنسبه للمعلومات، فسيكون البريدكشن بالنسبه للسينال موديل كذلك في لو كواليتي.
لكن هو الموديل بتاع حضرتك افيلابل ان هو يدخل لايرز جديده، بالذات اللي بتكلم على الدرينج عشان الهازارد والفولنربيلتي بتاعت الايفنت، سواء للدرينج او للسويل كاركترستيك، خصوصا الانفلتريشن.
كلما كان الانبوت غني، كلما كان الانبوت يعني بالنسبه للكلاسيفيكيشن نتعامل مع الداتا اللي تكون معتمده او available. اذا كان درين سيستم والانفلتريشن ريتس معتمده او available يعني ممكن الحصول عليها، فاعتمادها في الكلاسيفيكيشن موديل سوف تعطي نتائج احسن من عدم الاعتماد عليها. يعني كلما كان الانبوت ديتيل، كلما كان الانبوت افيلابل، كلما كان الانبوت يعتمد على انبوتس اللي influence or characteristic the flood dynamics، كلما كان البريدكشن احسن. اما بالنسبه للسياق في هذه الداتا ليست available or من الصعب الحصول عليها، فنعتمد بما هو يعني available، بما هو موجود. ولكن اتفق اذا كان الاعتماد على كل هذه الداينامكس بما فيها الانفلتريشن drainage سيستم etc، اقحامها في الانبوتس سوف يعطي نتائج احسن من عدم اقحامها.
شكرا جزيلا لحضرتك. شكرا.
Okay, thanks. Hello, I have a question.
اتفضل الحاج.
Good morning to everyone. Thank you for everyone, webinar and facilitator. And really, the lecture is I'm from Sudan, and there are a lot of floods, and I saw from the series of and through these lectures, I do have a question that it's that possible to establish early warning system using the machine learning through your modeling. Thanks for that, and this is all.
I'm sorry did
أعتقد السؤال كان يتعلق بهل يمكن تطبيق الإنذار، استخدام هذه النماذج في الإنذار المبكر للفيضانات.
بالطبع، خصوصا فيما يخص regression models، CNN models، surrogate models يعني النماذج البديلة. يعني ممكن أنه يتم التوقع السريع بالنسبة للفيضانات بناء على الرينفول intensity. يعني هذا is an example. If we can have the rainfall we can have even before a rainfall event. If we can have the rainfall, have the prediction 1 minute, we can delimit the high risk areas, which means that we can evacuate we can plan the emergency plans, we can do. So this is an application of the early warning system. So if we can predict fine details in 1 minute and before the calamity, we can, of course, this aids to an early warning system. This can serve as an early warning system in this case.
مع العينين أستاذ، واحد الدقيقة. مع العينين هي في الحقيقة الماشين ليرنينغ والذكاء الصناعي ماشي آلة سحرية. راه إذا ما كانش عندنا معطيات دقيقة وبيانات كثيفة في أزمنة مختلفة ومتعددة تأخذ بالاعتبارات جميع العوامل التي تدخل في الفيضانات، راه التنبؤات ما يمكنش تكون صحيحة. باش تكون عندك بيانات متنوعة وغنية جدا، لأن الذكاء الصناعي أو ماشين ليرنينغ كيستعمل خوارزمات، وهذه الخوارزمات كتحسب الوضعية التنبؤية مع الوضعية الحقيقية، وإلا كان الفرق بيناتهم ليغور، اون ابل سا ليغور، الخطأ، هامش خطأ دقيق، فالنتائج غادي تكون جيدة. وهادشي واحد البيج داتا مهمة جدا. وإلا حنا واش كنستعملو كما يكونوش عندنا البيانات، كنستعملو لي موديل ماتيماتيك ديترمينيست، كالكول نيميريكال كومبيوتد. كناخذوا بعض البيانات وكنستعملوها وكنغديو بها الخوارزمات ديال الماشين ليرنينغ، واحد النتائج نسبيا جيده. ولكن كان كانت عندنا نتائج ولا بيانات تاريخيه لازمنه مختلفه متعدده بسيناريوهات مختلفه، غادي تكون ان شاء الله نتائج التوقعات كتكون اكثر دقه واكثر فعاليه. دونك هذا هو كما نقولوا الاساس ديال الذكاء الاصطناعي، او او باللغه الفرنسيه لابرونتيساج اوتوماتيك. فوالا. شكرا.
شكراً أستاذ بوصحاب. أعتقد حضرتك عملت تلخيص مهم جدا للمبدأ العام. حينما يتواجد كمية كبيرة من البيانات مع نماذج التعلم الآلي سنحصل على نتائج جيدة، سنستطيع أن نصل إلى إنذار مبكر. لكن بدون بيانات كافية سنحصل على نماذج ضعيفة، ربما تتنبأ بشكل خاطئ تماما وربما تضر أكثر ما تنفع. فأعتقد هذه من أهم الرسائل التي يمكن أن نخرج بها من هذا الويبينار. أيضا أعتقد أن المحاضرة قد أشارت لأهمية أدوات التعليم الآلي، ماشين ليرنينج، والذكاء الاصطناعي، وكيف يمكن تطبيقها لدرء مخاطر الفيضانات. وأن هذا المجال مجال يمكن أن يكون هناك إسهامات كبيرة جدا فيه في خلال الفترة القادمة، وتوفير بعض الأدوات الرخيصة وباستخدام البيانات المتاحة لتزويد متخذ القرار بأدوات سريعة. لكن في نفس الوقت كما أشار الأستاذ بوصحاب والدكتور سيد مخيمة أهمية القياسات الأرضية لكي نستطيع أن نحصل على نماذج دقيقة. فبدون بيانات، بدون محطات رصد، لن يكون لدينا نماذج جيدة وقوية. أعتقد إن النهاردة كان معنا محاضرة شيقة جدا، وكانت بداية جيدة جدا للويبينار واختيار الحمد لله موفق. هل في أي مداخلات الآن قبل ما ننهي الجلسة؟ أنا في نهاية الجلسة أحب أشكر ماء العينين البيضاء على المحاضرة الشيقة، ونتطلع إن احنا نتابع تطور هذا العمل خلال الفترة القادمة إن شاء الله. والشكر ممتد للأساتذة، الأستاذ بوصحاب فريد والأستاذ ميمون شراق المشرفين على هذا العمل الضخم والمهم، والضروري أن يتم توسيعه على المستوى العربي. وده دورنا إن احنا نفتح مجالات للتعاون وتبادل المعرفة. شكرا جزيلا لجميع الحضور على الحضور، ونتطلع أن نلقاكم خلال الندوة القادمة إن شاء الله. شكرا جزيلا ومع السلامة.
مع السلامة.
شكرا. Thank you for
شكرا.